Hello students, hope you are doing well. In this topic, we'll look into the next topic of simple harmonic motion, and that topic is rotational SHM, and we'll look into an application which is physical pendulum. Now rotational SHM, under what condition we say an object is under rotational SHM? Now let's say an object is in rotational oscillation such that the torque acting on the object is directly proportional to theta and is directed towards the mean position. Then we say it is rotational SHM. I'll write tau is proportional to minus theta. If I put a constant, I'll write it as tau equal to minus c theta. Right, this is what is rotational SHM. Now tau can be written as I alpha, that is equal to minus c theta. From this I can write alpha equal to minus c by I into theta. Now when we talk about rotational SHM, we have angular acceleration equal to minus omega square into theta, where omega is angular frequency. Comparing these two equations, I'll have omega square equal to c by I, or omega equal to root c by I. Omega can be written as 2 pi by t. So I have 2 pi by t equal to root c by I, where I is moment of inertia and c is the coefficient of theta in the expression for torque. So we have t equal to 2 pi root I by c. This is what is the expression for time period in angular SHM. Now let's apply this to a simple pendulum. Now what are the forces acting? Mg downwards, tension. Now this is mg sine theta, and this is mg cos theta. Now let's look at torque acting on it. So torque, restoring torque is mg sine theta into L. This is torque. Now, so for small angles, if theta tends to 0, I can say sine theta tends to theta. That would imply torque acting equal to, there would be a negative sign because it is a restoring torque. Torque equal to minus mg into L theta. This is how we can write. So from this I can write C equal to mgl. Now what is moment of inertia of the system? I equal to m into L square, because the axis is at a distance L from the mass. Now let's find time period. T equal to 2 pi root I. I is ml square by C. C is mgl. So mm cancels, ll cancels. That would imply T equal to 2 pi root L by G. So this is an example where I've done the same thing that we have done previously without taking into consideration angular SHM, so that we can understand easily how angular SHM can be applied. So in this way I find the torque, and if I see that torque is proportional to angular displacement, then I find out what is the coefficient of angular displacement, and then I put that in the formula T equal to 2 pi root I by C to get the time period of the angular SHM. Now let's look at one more application of this, a physical pendulum. Of course here, so physical pendulum is something where the whole body is there right from the top to bottom. Now let's say I take a physical pendulum and slightly disturb it by angle theta as shown here. Now you can see here the forces acting is, this is mg cos theta, this is mg sin theta, and this is mg, and this is 10. Now if I look at the torque acting on it is tau equal to mg sin theta into, I'll say L, where L is the distance of the center of mass from the point of suspension. So again, if theta is small, then I can write sine theta tends to theta. Then tau would become, I'll write minus because it's restoring torque, mg theta into L. Or I can write tau equal to minus mgl into theta. So here C equal to mgl. Right? Now, if I'm talking about this, if it's a linear rod, generally physical pendulum is linear rod. So first let me write down the expression for time period. Time period is 2 pi root I by C. So I by mgl. Now if this is a rod of uniform cross section, so I say this is a rod of uniform cross section of mass m, then the moment of inertia of the rod would be I equal to ml squared by 3. Moment of inertia of a rod rotating about an axis passing through one of its ends is ml square by 3. So if I substitute that, I'll get T equal to 2 pi root I by C. That can be written as 2 pi root I is ml square by 3 by C is mgl. So mm cancels, 1l cancels. So we're left with t equal to 2 pi root L by 3g. So this is time period of the physical pendulum. So in this way, this question can be easily solved by using angular SHM. So there are a lot of questions which can be solved using both angular SHM as well as linear SHM. We have to be judicious in identifying which method would get us to the answer with least confusion and least time. So this is about angular SHM. So let's have a quick review of what all things we have done. We have defined angular SHM. Angular SHM is the oscillation, is the angular oscillation in which the restoring torque is directly proportional to the angular displacement and is always directed towards the mean position. Then we found an expression for time period of angular SHM which is equal to 2 pi root I by C, and we applied the concept to a physical pendulum. Of course, a simple pendulum to understand how does it work, and then to a physical pendulum to find what is the time period of a physical pendulum. So this is what is there in this particular topic. Keep watching other videos for other topics. Thank you very much for watching Get My Class videos. Thank you very much once again.